worksheet before the quiz. Can I have the worksheet? Sorry. I know we did the entire thing together. Yeah. Oh yeah, there was also a homework. Can you, first let me collect this worksheet. Okay, worksheets, sit back down. Alright, there was also a homework which which we didn't really go over. I think we did like one problem, and it was like the half day or whatever. So, I don't know, I thought there were like 2 or 3 problems. This is from section 9.3. This is from the textbook. This is page 314. I thought we could do like number 38, 44, and either 47 or 49. 49 really quickly. So 38 gave you 3 integrals. It told you that the integral from 2 to 4 of x cubed dx was 60. It told you that the integral from 2 to 4 of x dx was 6. And it told you that the integral from 2 to 4 of dx is 2, although I didn't really need to be told that. And then it asked you to compute an integral. And the integral actually compute was the integral from 2 to 4 of x cubed plus 4 dx. There's probably one really easy way to do this.
So split it up.
Or even just split it up, right? If I just rewrite this as the integral from 2 to 4 of x cubed dx plus 4 times the integral from 2 to 4 of dx, then this is, because they told me 60, and this is 4 times 2, so it's just 68. That's pretty easy. I don't even know if we needed to do that. 44 was a similar kind of a problem. They tell you that the integral from -1 to 1 of some function is 0, and they also tell you that the integral from 0 to 1 of that function is 5. And then they ask you to answer all of these questions. Okay, so we have to be careful about this. You might be tempted to draw the following picture. The picture you might be tempted to draw is one that looks like this, where you go, that's 1, that's -1, and maybe something like that. And then you might say, okay, well that has area 5. Is anyone tempted to draw that picture? Seems tempting. However, that's potentially misleading picture. Because just because the integral from 0 to 1 of some function is 5 doesn't necessarily mean that the function is positive here. There could be some positives and some negatives that balance each other out. So, before I erase this, you guys have this, see what I'm talking about here? So it is probably more safe to draw a function, if you are trying to draw a function, which is sometimes positive and sometimes negative, and whose difference is 5. So maybe let's call that area 7 and that area 2. Do you guys see the difference with what I just, subtle difference with what I just did? Okay, so anyway, this is going to be the kind of picture that I'm going to sort of be thinking about, that maybe my function looks something like that. Alright, then it asks you a whole bunch of questions, like, what is the integral from -1 to 0 of this function? Well, if the integral from -1 to 1 is 0 and the integral from 0 to 1 is 5, then the integral from -1 to 0 must be -5, right? Comments? Thoughts? No. Right, how about B? B is the integral from 0 to 1 of f minus the integral from -1 to 0 of f. Well, I guess I can just do those both because I just did them, right? this is going to be 5 minus -5, so that's 10. Is that what you got? Okay. C. C says, this is more sort of properties of integration. What's the integral from -1 to 1 of 3f of x? Well, that's just 3 times the integral from -1 of the function, so that's 3 times 0. So that's just 0. And finally, am I doing this right? Oh yeah, this is actually not that hard. The integral from 0 to 1 of 3f of x is just 3 times the integral from 0 to 1 of f of x, so that's 3 times 5, so that's 15. Raise your hand if you got all 4 of these right. Okay, that's pretty good. Let's do either 47 or 49.
49.
Okay, 49 it is. 49 is a similar kind of problem. It says, take some function such that the integral from 0 to 5 of that function is 4, and now answer a whole bunch of questions. Question 1, what is the integral from 0 to 5 of f of x plus 2? Well, the simplest thing to do here is to just split it up. This is just the integral from 0 to 5 of f plus the integral from 0 to 5 of 2. And that, you just told me, was 4. And this is just 10. So it's just 14. Even not cool?
Cool.
Okay, part B says, what's the integral from -2 to 3 of f of x plus 2 of that function? Well, now we've kind of seen this trick now, right? This just moves the whole function 2 to the left. So this is just going to be the same, right? Because it's just a shift. Comments about that? I've never asked any questions. Are you shy, scared, smart, so you don't have any questions? All of the above. Alright, integral from -5 to 5 of f, and now they tell you, oh, by the way, f is even. Well, if f is even, then this just has to be 8, right? Because it's just the same thing on both sides. Okay. And finally, what's the integral from -5 to 5 of f if f is odd? Well, then that just has to be 0. That's something we've talked about. All right, other questions from this homework? Can I have this homework? Can we put it right here?
You're my number. Oh my God.
All right, finally, we get to do something. As I promised, this is the second most important day of your life, but it probably hasn't felt like it so far.
It is not.
We have 30 more minutes to get into some serious business. Actually, it probably is not even enough time.
I screwed up the I.
Oh.
Even if it doesn't happen today.
Okay. There's this thing called the midpoint rule. All right. What does the have we talked about the midpoint rule yet? The midpoint rule basically says, instead of using the left-hand endpoint or the right-hand endpoint, just use the midpoint. So let's take some integral, like the integral from 1 to 2 of 1 over x dx. Okay, this is not a polynomial, so I don't know how to do this. If I were to try to do this and to draw a picture, this is going to be 1, this is going to be 1/2, and if I were to try to split this up into a whole bunch of little subintervals and try to use summation formulas, that would fail because I don't have formulas for 1 over n. All right, so I'm going to have to try something else. And the something else, unfortunately, at this point, is just we're going to have to estimate it. So here's my goal. My goal is to approximate this interval using the midpoint rule. Using the midpoint rule with n equals 5. In other words, let's split up this interval into 5 equal width subintervals, and then let's approximate using the midpoint. Alright, so let's make a big picture of this, so it's very clear what's going on. Here's 1, 2, like I said, here's 1. Plug in 1, I get 1. When I plug in 2, I get a half. So this is my function. And this is the area that I want. Okay, so let's split this up into subintervals. 5 subintervals. So what's the width of each subinterval? 0.2. Okay, so this is not that hard. I get like 1.2, 1.4, 1.6, 1.8. That looks pretty decent. But now, on each one of these subintervals, instead of drawing a rectangle whose height is the left endpoint or the right endpoint, let's let our sample point be the midpoint of those two. And if you do this, you see that it's like a kind of good, right? Good things sort of happen. Because if I plug in, so now I take the midpoint of each one of these subintervals, and you should get kind of pretty...
It's like a mix of Riemann and
It is its own thing. You can think of it that way. But it's really like its own thing.
like it goes above and below.
It's MRAM, yeah. At least for this particular case, it does go above and below.
Well, it cancels out.
Exactly. So Ethan Lott is observing what you should all be observing, which is the beauty of this using the midpoint is if my function is monotonically decreasing, then this midpoint approximation is going to be much, much better than either an approximation using the left endpoint or an approximation using the right endpoint, assuming I keep n equals 5. Because some of what I miss on the left interval is gained on the right interval. Is this clear? Okay. So how would we actually, so what is this area, approximately? Can someone like tell me, start calling them out, right? Like what is it basically? Or maybe we want to go straight for the sigma. No, maybe not. What is this area?
2
Okay, yeah, the area of the first rectangle will be 0.2 times the height, which is
1 over 1.1.
1 over 1.1, because 1.1 is the midpoint of the interval between 1 and 1.2. Okay, the next rectangle will have area. Come on, you just do it all.
What? No.
Everyone else is scared of me or something. Dana, next one. Correct. Next. Yeah, keep going, yeah. Okay, and the last one.
Dude, that was silly. There's only 1 in there.
Oh yeah, so I only skipped 1. Anyway, I did get, but I got kind of bored. All right, so can somebody write this out in sigma notation? It's actually a little bit hard. It's just a little, it's not hard, it's just like a little kind of computer sciencey kind of thing where you like have to think about what you're doing. So you can factor out a 1/5, and then the height of the ith rectangle will be
I can do it. 2 I might want.
1 goes to 1.1. It's 2 to 1. Just 2 and goes 2 and goes 1.
Minus 1 over 10.
Okay, it's not that hard. I need to somehow write some formula for this bottom such that it's when I is 1 it's 1.1, when I is 2 it's 1.3, etc. What is it? What?
2.9 plus that's the decimal.
Thank you. Jesse. Say it again?
0.9 plus 0.2 times I.
Yeah.
Oh yeah.
It's just like a little kind of computer sciencey thing, right? Make your loop so that it like matches up. When I is 1, you want that to be 1.1, so that's like, you know, I have to add 0.2 to something, so the thing I better be adding to is 0.9. And by the time when I is 2, I need to be moving over 0.2 each time. Is everyone okay with this? I mean, I don't know, that bad. Okay, so I could either compute this out, or I can do something cool. Let's use our calculator to do this for us. And I'm going to teach you something which you may have never seen before. I'm sure, in fact, I'm pretty sure you've never seen it before. It is this so-called this sum sequence command. Are you getting a shot on the TV?
Yeah.
All right. I have to like not walk in front of the camera. All right. So, we'll go over here. So let's do this. There is this command. If you go to second stat, this brings up the list menu. Everyone try to stay with me. Can everyone like actually do it? Unless you really, really don't have a calculator, in which case you should be looking at another person. Okay, so if you go second stat, it brings up the list menu. If you go over to operations and you go over to sequence, your calculator will be able to construct a sequence for you. And you can define what the sequence looks like. So for example, what if I want the perfect squares from 2 to 7? Then I say, all right, well my formula is x squared. And then you have to comma, the next parameter is the variable which you increment with respect to. So we're going to increment with respect to x. And then we're going to go from x equals 2 to x equals 7. Does everyone understand the syntax? I'll give you one example. All right, and that is going to output a list of the perfect squares, you know, from 2 to 7. Okay, looking pretty good. So, how could I do this thing over here? How do I make the sequence of these numbers? Well, I can just like do it, right? Now I'm going to do second stat sequence, and now I'm going to go 1, the sequence should be 1 over, as Jesse figured out, the formula should be 0.9 plus 0.2x. You guys following this? That is the formula that we determined, comma what? X, comma 1, comma 5. And what is that going to do? It's going to construct a sequence, each of whose values are the things which I'm adding up. So that is 1, that's 1/11. Oh, wait, did I do something wrong? No. That's 10/11ths. Yeah, that's 10/11ths. That's like, whatever it is. These are the numbers. Okay, and now what I really want to do next is I want to add up all those numbers somehow, right? Say right. So there is a method to do that also. If you go second stat again, operations, math, so not operations, second list math, sum. The sum command will take the sum of the entries in any list and we'll just add them up. So if you go sum, answer, that is going to be that summation sign. And then, what do you do next? Yeah, just divided by 5. Ta-da! And we get 0.62. Does 0.692 seem reasonable answer given that this is a square of area 1?
Yeah.
Okay, cool. That is not the exact answer, by the way. It's just an approximation. Okay, so this approximating technique is precisely what we can do when faced with a function which is not a polynomial. Alright, so now comes an important moment in your life, which is we are going to answer a question which you've been dying to figure out for years now. Ever since someone first drew you the sine function, you have probably thought, man, I wonder how much area there is under one hump of the sine function. Alright, could I get some estimates?
1.
1. Is that a good estimate? Maybe. It's not terrible, because this is about 3 and that's about 1. So okay, ballpark. I mean, you know, there are worse answers. 2 maybe is a little bit better. What's it definitely less than?
3.
Definitely less than pi. So let's just say that the answer is somewhere between 1 and pi. No, I probably can get rid of these equal to's also. The answer is somewhere between 1 and pi. All right, how can we do this? Well, we can split it up into a bunch of subintervals. This time, let's use Rm because once we have a calculator, you know, who cares? So let's, or should we do it? Let's do it with n equals 10. Okay, if we do with n equals 10, then what's delta x?
Pi over 10.
Oh, what am I? This is not a hard question. If n equals 10, that means I'm going to use 10 rectangles. The total width of the interval is pi, so delta x is pi over 10, thank you. So now let's draw some rectangles, not necessarily to scale. This first rectangle will be like, that's like pi over 10, right? Say right.
Yeah.
And then that's like 2 times pi over 10, and you know, et cetera, et cetera. So can somebody write me out a sigma notation expression for the area under this curve as approximated with 10 rectangles using Rm? Christine says take the pi over 10 on the outside to n, or 10, because I'm doing 10 rectangles. Sine of pi over 10I, I think, right? That's it. Yeah. Each rectangle is going to have width pi over 10, each rectangle is going to have height, sine of pi over 10, sine of 2 pi over 10, etc., etc. Okay, well, I certainly do not have a formula which will enable me to do this exactly, but if I'm just doing with n equals 10, then I'm just going to use my calculator, because that seems like a good idea. So let's do that. How would I do this? Can we do this the tough guy way, where we do it all in one big step? All right, so what should I write? Pi over 10 times the sum of, so second stat math sum, and I want to sum up a sequence defined by pi x over 10. No, sine of that. Oh, make sure you're in radians, otherwise this whole thing becomes a joke. So the sine of pi x over 10. Oops. Pi x over 10. Close the sign. Then what? Comma x, comma. No, I'm starting with 1, I think, this time, right? Comma 10. Close the sequence, close the sum. Drum roll. Whoa! 1.98.
I was really close the second time.
I win. Okay. Bearing in mind, of course, that this is not actually the answer, right? This is simply an approximation of the answer. How can I get a better answer? More rectangles. What are you guys laughing about? Can't be that funny. All right. If I have the happy box in my hand, then I might as well. Why stop at 10? Why not do more?
100.
You getting all this? Yeah. Let's go to 1,000. Let's do 1,000.
My calculator won't do that.
Oh, really? Let's do 1,000. So I have to change this 10 to 1,000. I have to change this 10 to 1,000 also, and I have to change this to 1,000. Wacha! Oh, is this what's happening to you? It takes a while. It's kind of slow. This is a riveting video going on here for period 3. So I should have listened to you and just done 100.
I did 100. It was 1.9998 something.
All right, I'm quitting. Has anyone? Does it stop eventually?
How do you break out?
Okay. All right, that seems too hard. Let's try. Let's do 100. Wacha. Whoa! 1.9998. All right, raise your hand if you think that the true answer is 2. Yeah, I do. Okay, good. So, Diana, is there one button which will just do this whole thing for us? There is. It is called functional numerical integration. And it is located under the math menu. If you go to math, this calculator will do any integral for you. Math 9. It says FN int. That stands for functional numerical integration. Integration because it's integration. Numerical in the sense that it's just cranking it out. That's kind of what numerical means. And functional, I don't know, you give it a function. Okay, so here are the parameters for functional numerical integration. You give it a function, like sign, comma, you give it the variable that you are integrating with respect to, and then you give it the lower, what?
I want to do like pi over 10.
No, pi over 10 was just the width of the interval. Now we're just doing it, man.
We'll do it straight up.
This is straight up. The integral, we're taking the integral of sine from 0 to pi, right?
Yeah.
Ta-da! It is exactly 2.
This is so cool.
It is very cool. Okay, what time is left?
Wait, but this
Forever. What should we do?
Let's do
We have 10 minutes. Okay, man, that was like a half an hour more I planned to get accomplished today. This is what happens when I overplan. And alright, so we're gonna do one last activity, which involves everybody having both of these worksheets. Can you give everybody one of these? Can you give everybody one of these? One of these, can you stop talking? One of these worksheets that you're getting is the integral, just asks you to do the integral of x squared from a to b in general. So this is just the kind of exactly like the quiz we just took, but now, instead of giving you particular numbers, I'm just going to give you general numbers. Oh, and by the way, we are now in the FTC is imminent now, okay? It is imminent. That means that suddenly, depending on circumstance or your individual brain, the FTC is going to just kind of come to you now, suddenly, in flashes. And if that happens, I please ask you to keep it to yourself, because it is important that each person have the opportunity to let the FTC into their brain, heart, and soul at the appropriate time that's right for them. So, if the FTC suddenly comes to you in a flash, just like hold back and let everyone have their moment. I'm so jealous of you guys. It's like, there's only one time that you can learn the FTC for the first time. It's like, it's just a special moment.
That's like this thing. People were like, I wish that they could like delete sections of memories.
All right. Yes. Okay, so here we go. I am now going to define to you this. I'm going to do this very strange thing now. I'm going to define to you a function, and this function is called an accumulator function. Accumulator function. Alright. And an accumulator function is a function such that when you plug a number into that function, it tells you how far you integrate. And now what we have here is some other function, f. And I'm going to try to draw f right now. It's on your paper. So this is 2 lines, and then it's a semicircle, and then 3, 4, cha-cha-cha, and then that's like 7, right? 8, 9, 10, and that's just flat. Okay, so first of all, everyone stay with me. I think we have just like 5 minutes, right? Everyone staying with me. This function that I've just drawn is f. Everybody? Good. G is a different function. G is a function which says integrate f from -4 to some other spot, and I'll tell you when to stop. Right? Okay, so let's just compute some of these. Everyone do this right now. What is G? Compute all these guys on the right-hand column. Go. Guys get what I'm getting?
Isn't it plus?
What's up?
Isn't it 4 plus?
These are-
Oh,
these are
yeah.
upside down.
Oh, yo.
So that's gonna be 4 minus 2 plus 2 I got these numbers. Is that what you got? Just by adding up a bunch of area, right? The integral from -4 to 4 is just 0. The integral from -4 to 2 is just the area of this triangle, that's 2. From here to here, it's the area of this triangle, that's 4. Is that what I mean? Can I keep going? Okay, now here comes a deep question. On what intervals is G increasing? Okay. What does it mean for a function to be increasing? It means that as you move to the right, the function is getting bigger. So let's imagine that we're over here, right? And I start to draw a rectangle. Did my g function just get bigger?
Yes.
This is deep. Yes, my g function just got bigger because I added more area to it. That's why it's called an accumulator function, because you're accumulating area. I just drew another rectangle. Did my g function just get bigger? Yes. Is my g function getting bigger as I draw rectangles? Yes. How about now that I just drew a new rectangle, but that rectangle is shorter. Is g still getting bigger?
Yeah.
G still is getting bigger. It's getting bigger at a slower rate, but it's still getting bigger. Okay, now what happens when I start getting over here? Now what happens? Yeah, now I'm drawing a negative rectangle. And what happens every time I draw a negative rectangle? It's like I'm adding a negative thing to my sum, right? So what's happening to G now?